Good morning, everyone. So for those that don't know me, a little bit about myself. I'm CEO of Goldratt Research Labs. I had the incredible privilege and honor of meeting Dr. Eli Goldratt when I was about 21 years old. And part of the story I'm telling today is some of that excitement of after reading the goal. Everybody gets some type of major insights. I'm going to share with you what are the major insights that I got from that book. I had the privilege of working with him for over 25 years. We did incredible projects together and finally ended up co-founding the Goldratt Research Labs back in 2008. What we do is very simple. The organization is just working with companies from both private and public sector to answer three simple questions. Can we do better? And the answer is always yes. How much better can we do? And how to do much better? Just by changing the rules that we use for managing the system. At Goldratt Research Labs, we study why good people make and often repeat bad decisions. And as you can imagine, this is a topic that's close to all of our hearts. If I get into an Uber and I tell them what I do, they go, oh my goodness, you can make a whole research out of my own life, because we all make bad decisions. We often repeat these bad decisions, and for a different number of reasons. So some of these reasons are we get overwhelmed. Some of it is we don't realize the impact that our emotional biases and blind spots have on our decision making. But there are also some types of decisions that really we cannot make. We simply do not have good enough intuition about the complex world that we live in. And that's really what today is going to be all about, is to share with you some exciting examples about, first of all, how can you think about a system versus a subsystem? So our title is, we should focus on the system constraints, but do not forget about subsystem constraints. What do we mean by that? What is a subsystem? I'll share with you a little bit about that. And then I'll talk about the VUCCA challenge. Most of you would have seen this acronym. I added another C to it because I think that there's a key part that's missing in the VUCCA definition of why it's so challenging to manage real-world environments. And I'm going to share with you two of the initial simulation models that really changed my life. It's often interesting when you at a kid's party and somebody asks your kids, what does your dad or mom do? I don't know if you've ever had that opportunity to kind of peek in and hear what they say. And my youngest gave a really elegant definition once. He said, my dad builds computer games and show people how to get high scores. So I'm going to share with you why that is the case. And then I'm going to go into two very interesting case studies. I've had the privilege of working with some of the most incredible companies and teams around the world, but these ones are especially special, and somebody that's been a partner that invited me in is Bimlendra Jha, my co-presenter. Unfortunately, he couldn't make it today, but he's got two video clips where he'll share with you some of his own unique insights in terms of our collaboration. So he's going to be talking specifically about two parts. One is the Tata Steel India and UK collaboration, where both of those involved building quite sophisticated simulation models for them to understand what is really the cause of the big gap between what their expectation is and what reality was, and how to close that gap in the lowest cost, lowest risk, fastest possible way. And then a new project that we worked on last year and the beginning of this year, Jindal Steel, two absolute empires and legends within the Indian market and steel production. I'm going to share with you then my take sort of as a summary, some of the key takeaways, and also about how can you maintain focus on the one thing. So we'll start off with just a brief introduction from Barnard.
Hello everyone, and my sincere apologies for not being able to join you in person at this TOC ICO conference. And thank you, Alan, for standing in for me. You have been a friend alive in my 20 years journey in TOC ever since it began at Tata Steel as an integral part of Aspire program, where we were already running it with Six Sigma and TPM, or what is called as lean principles, and we integrated TOC. Since that day till now, we have had several occasions for collaboration, and all this collaboration has brought us to some new understanding about how best to implement the principles of TOC and what role simulation modeling can play. I must say that wherever I have applied TOC, I found it quite simple and easy to apply, except that many a times there have been circumstances where I didn't even know where to apply it. And the first time I saw kind of a moving bottleneck phenomena, it was in LD1 shop, which is a steel melting shop of Tata Steel at Jamshedpur. And subsequently, when I went to UK, I also found similar moving constraints. And this time, it was not merely some physical asset that was becoming a constraint in a small shop. It was in the entire supply chain that subsystem level constraints started developing. And subsequently, back to India in Jindal Steel and Power, I could experience something similar. And every time I looked at Alan and his team to come and try and simulate this reality for us. Because in TOC, we are all aware of 5 focusing steps. The most difficult thing, as we are all aware, is that when this constraint shifts at the system level, we can even decide how to exploit, but changing the subordination rules is very difficult. Simulation modeling has not only told us that subsystem levels can become moving bottlenecks for the system as a whole, it also has given us a preparation time that is necessary, not only in terms of what to change, but also the entire change management that is necessary so that people are aware that when the constraint shifts, at that time what to do and why to do it. I think Alan will take you through all these stories, but I must say that the most interesting aspect of this entire change has been that you can almost foresee reality. You can plan for the future when the future is completely uncertain, but you can do it using the stochastic methods. Not only it allows you to check the future, sometimes the mystery hunting that we have learned in TOC for why our expectations are not meeting our reality. We can also run it on the past events and check where things have not really worked as per our thought process. I will leave it to Alan to take you through this exciting journey where we have talked about focusing on the constraints but ignoring the subsystem level constraints at your own peril. Thank you very much.
The key insights of theory of constraints was that you can actually analyze and manage and improve the whole system by analyzing, managing, and improving each constraint of that system. So what does a system consist of? It consists of a goal. The goal, which could be an impact goal or an income goal, determines the work that has to be done. What products or service will the system produce to achieve more of the impact or income it is trying to generate? The goal and the work also dictates the process that we're going to be using to make the work, to produce the products, to produce the services. It defines the steps, it defines the dependencies, whether you're in a production or operations or project environment. It also defines not only the resources you need, but how much of every resource you need. And there's only 5 types of resources we need for managing organizations. We need enough demand for the products or services we provide to achieve the goal. If we don't have enough demand, we have a demand constraint. We need enough capacity and capability to deliver enough of the work. We need enough supply, external resources. We need enough cash. We need enough management attention. Any resource we do not have enough of is a constraint. And just a reminder for those, I remember when I was marking the fundamentals exam the first time we offered it at TOC-ICO, the most common mistake most people make when they're defining the 5 focusing steps, they forget to put in the S in brackets. Step 1 is identify the system constraints, not constraint. And in fact, the first time Dr. Goldratt verbalized this, he made a note. He says, I'm putting it in brackets because having a single constraint can happen in simple situations. The more common situation is you have multiple constraints. If you're overloading one resource because you've overcommitted and you have very much balanced systems, it's very likely that you've overloaded multiple resources. So you have to be very careful there to not just think about one weakest link, one constraint. Think about, I have a goal. The goal requires me to have a certain amount of resources across all those areas. What don't I have enough of? That is my system constraint. I then have the last 2 parts, which is what are the rules I'm going to be using to manage the flow of work through the process and to manage the resources. And I have different rules. I have rules for deciding what the design of my system would be like. And I'll share with you an example of what does a supply chain network look like? What is the most optimum? That's a decision we have to make. We get it right, it could be highly profitable. We get it wrong, it could be very unprofitable. We have to make decisions around pricing of our products and services. We have to make decisions about how we will plan and execute and improve. By far the biggest leverage points in the system is just changing the rules. Not changing the work that we do, not changing the process that we follow, not changing the resources, just changing the rules that we use to manage the flow of work and resources. And then the last part of a system is there's measurements, and these measurements are three types. There's lag measurements telling us if we are achieving more of the goal, the impact and income. There are lead measurements that tells us why. So the lag measurements, are we okay? Are we achieving our goal? The lead measurements is why are we not okay? And then we also have compliance metrics, a very important part, because if I'm not achieving the outcome, I want to know, is it because I'm not following the right rules? I need to change the rules, or is it simply non-compliance to the right rules, which can frequently happen? And then we have to investigate why are people not complying. So this is just a very simple way of thinking about a system. Now, that layer there could be multiple subsystems. So you can imagine the goal of the organization creates a demand on the HR department. The work that they do is hiring new candidates. It puts a demand on the finance department. The work that they do is process transactions, manage the cash. It puts a load on the operations, etc. So as you're going through that, what you want to do is the 5 focusing steps can really apply at the company level, but at any subsystem level. And the simple question is, do I have enough? My role as a manager is to make sure the work that the system puts on me is getting done and that I have enough resources to get it done in time. I hope that provides some clarity, especially for the newcomers, of how to think about it. So the constraint can be at the system level. Overall, we don't have enough demand for our product or service, and I have to address that, but it can be from time to time that the HR, as a result of some budgeting constraint, they might not have enough resources to cope with the demand that the system is putting on them. So let's look at what makes life interesting. I mentioned this VUCCA conditions. The first one, V, is for volatility. There's going to be variability in demand and supply. And what I'm going to show you with these very simple simulations that you will recognize is how just 2 of these factors suddenly makes life very interesting. So you have volatility, uncertainty. We can't predict really what the causes of certain things are. We can't always predict the effects. We can always predict the range of the effects which a simulation identifies. But why I say you can't predict the causes accurately is small changes can have big impacts, right? You suddenly see your profit drop or increase by 20%. You might be looking for something big, where in fact, if I have a company with a sales of 100 and profit of 5, just a 1% change in the average selling price would add $1 million to or take $1 million away from my 100 million revenue. That will drop to the bottom line, and that can cause a 20% shift in my profitability. One of the things I'm going to encourage you is to think about simulation as one of the key tools that you have in your toolbox to understand causality. Because small changes can have big effects. And normally when people are building CRTs, they don't have intuition that small things can have big impacts. This is why the original program was essentially displaying simulators to allow people to discover the causality. It wasn't presented to them as write down UDIs and build trees. It was play the simulator, discover it for yourself. Complexity is the fact that there's lots of interdependencies between parts, substitutions. If they don't buy this, they might buy something else. If there's starvation here, it can cause a problem later on. Constraints is the one that I've added. 2 types of constraints that I'll expand a little bit later. I think about it as a flow rate constraint and a flow time constraint. There's 2 dimensions of flow. If we have a flow rate constraint, it means that we need to make more to achieve the goal. If we have a flow time constraint, it means we have to do it faster. We have to reduce the time to be able to generate more goal units. So 2 types of constraints. And the last one is ambiguity, is that we are always trying to optimize for multiple factors. I want to increase throughput, improve quality, reduce costs, and reduce investment. Well, which one do you want? With simple optimization algorithms, pick one number, it can give you an optimum answer, but it really struggles when you have trade-offs, and that's where the simulation comes in. We can see how by focusing on one area, it can impact others. So the problem is these VUCCA conditions exist. All the IT systems that we have essentially use as averages. They don't allow us to fully consider these VUCCA conditions when we are making commitments, when we are making decisions, and as a result, they often result in us making unreliable commitments. And I'll show that with you for the simple, even with simple simulation models, you'll see how easy it is. It also causes us to often make decisions that benefit the part and not the system. How do we solve it? We build simulation models that increasingly are enabling us to model the full range of VUCCA conditions. So we can fully consider real-world conditions when we are making commitments, when we are making predictions and decision-making. It combines today the latest advances in computing power. In simulation modeling, we can embed best practices, allow you to compare multiple different options, min-max versus TOC versus DDMRP, and it also more and more builds in human in the loop and AI. So a little bit of background. This is, I read the goal in 1991. I got addicted. The first thing I did was build a little simulation model about the dice game. I didn't want to just play it with dice. I want to be able to run it thousands of times and see what I can learn from it. So I'm going to share with you some key insights. Hopefully, even to the experienced TOC experts, there will be something new in that. And then the second one I heard was the first time I met Dr. Goldratt in 1992. He did a big group, mostly C-level people. He got us to play the P&Q example, and everybody got it wrong. And that intrigued the heck out of me. So I became very excited about simulation modeling, but also quite nervous because you're starting to wonder, is there any decision I can make where my intuition is strong enough? How simple must the system be for my intuition to guide me in the right direction, if even in simple cases, it's so easy to get it wrong? So let's share some simple cases. Most of you might have seen the dice game. So you think about this, a simple process that can represent anything. You have 5 process steps. Each can do 3.5 per day. We're going to run it for 100 days. And the question is, what will be the output? If you're using any traditional system that will use averages, it will say, oh, that's easy. You have a constraint resource. Well, they are all constraints. They're all perfectly balanced. Great system. 3.5 per day times by 100 days is going to be 350. So that's going to be the commitment that we'll make to customers and to shareholders. We can also just use some basic common sense and say, well, if I also had to commit to a flow time, so imagine the first batch goes into process A, after a day, 3.5 comes out, and it moves to B, C, D, E, then, well, it will take 5 days for a batch to go through. And then, well, how much work inside of the system do we have at any point in time? Well, if there's no buffers here, so those little buffer boxes are 0, you're not allowed to build a buffer, then the work in process is simply what's inside of the machines, which is 5 times 3.5, which would be 17.5 units. So now I've made a commitment around my output or throughput. I've made a commitment around time, and I've made a commitment around work inside of the system, my working capital. And I can quickly use Little's law just to check that my intuition was correct. Little's law says the total work inside of a system is equal to your flow rate plus the flow time. It warns us, and for many of you, this might be new. It doesn't talk about work in process. It's work inside of the system. There's 3 components to that, which is the work in the backlog, sitting in front that hasn't yet been released, the work inside of the system, which is the processing work that's sitting in the machine, and then the work in queue that's in between. So the work inside of the system is all 3 of those combined. And it says that's flow rate times flow time, so we have 3.5 times 5, so it accurately predicts the work inside of the system. If there's no buffers allowed, it would be 17.5. Now the question is, what if this 3.5 is just an average, and it comes from a variability in daily output represented by a dice throw? Can vary between 1 and 6. So the average is still 3.5. Will you change your commitment on any of those 3 levels? Will you change your commitment in terms of the throughput potential of this system, its lead time or flow time, and its work inside of the system? And this is the first part where I get linked up with Tata. So I get invited. We have a viable vision contract with them. I'm responsible for the training. I get pulled in, oh, there's a few people that want to ask you a question. We were supposed to just do some contract discussions. I get pulled into this room, 60 people. I said, what's the issue? I said, well, our constraint is capable of doing 3.5 million tons. We are committing to 3 million tons a year. I said, why 3 million? Because operational equipment effectiveness, a good target is 85%. So 85% of 3.5 million is roughly 3 million. So that's what they allow us to commit to. And I said, what's the problem? I said, we're getting on average 2.8 million. We don't understand why. And you can imagine I'm just going, oh my gosh, those numbers are almost exactly what we have in the dice game, right? 3.5 million, 3.5, that's supposed to be the commitment that we're making. And I said, I showed the dice game and I asked people, there were 60 people in the room, can you tell me what you would commit to in these three numbers? And the range of commitments varied all the way from the ridiculous on the one side, I'm going to commit to 400 because we have to have stretch targets, you know, all the way to just 100. The consensus was around the 300 level. I said, okay, let's play the game with zero buffers. What do you think will happen? You have zero buffers, so A throws a 6, B gets a 1, only 1 can move. The other 5 is just potential, it's gone forever, right? There's no buffer to put it into. You have a flow rate suddenly of rather than getting 350, you're getting 160. It's less than half of what you expected. Your work inside of the system is 190 after 100 days, because remember, we launched 350, we only got 160 out, so the difference is the 190. So float time 190 days, and most of that stuff is in backlog because there's no space to put it inside of the system. Remember, there's zero buffers. So then you say, well, what if we just added a buffer of 1? We allow 1 to build up in between. This is very interesting. Think about what would you have committed to. Just adding a buffer of 1, how much more could you produce? This is where our intuition fails completely. You add a buffer of 1, you go from 160 to 210. That's a big jump, just adding 1 size buffer in between each of the processes. You go to 5, you get to 280. That is where they were about. They were producing about 2.8 million tons. They were committing to 300, but their constraint could do 350. Everybody follows along so far? Can you see how even this simple system, really, really hard to make reliable commitments? Because what do I need to know? I need to know not only the constraint capacity, its average capacity, but I need to know the variability and the interdependencies. 3 factors of VUCCA. And it makes this a nightmare, even with a simple thing. And this is one of the things I discovered quite early that I was super excited to show earlier, is to say, if we want to commit to 300, how do we get there? Well, you can reduce the variability. That will take a lot of money and time. You can keep on increasing the size of the buffers and building up work in process, but it counts against you because now your lead times go up and up and up, and it costs a lot of money to do that. What if we created a constraint and we stopped C from throwing 6s? So its average drops to 3 per day. Will we get more or less? Imagine you're in a factory that's already underperforming and somebody walks in and say, to get more, you should slow down, right? But think about what's going to happen here is that A and B can still run at 3.5. So they actually have protective capacity to build up a buffer in front of C. And D and E can still run at 3.5, so they have protective capacity to make sure that the buffer behind C is always empty. And if C is never starved or blocked, it will produce at its capability, right, which can do 3 a day. And this is what happens. You get on average about 290 coming out of the system. This blew my mind. Now, I might be super nerdy, I don't know about you guys, but this absolutely blew my mind. And this essence of the solution is what we ended up implementing at Tata Steel. Next example, P&Q. So this is coming from the haystack syndrome, right? So all of you have played the P&Q before? Show of hands. Yep. So it's a brilliantly designed game, right? You go in there, you're so confident. Ellie gives you this example. He says, you know everything about the system. You know the demand. There's 100 demand for P, 50 demand for Q. You know the price. You know the OPEX. You know the cycle times for every resource. There's no variability in this case. There's no uncertainty. Machines don't break down. It's purely complexity, which is interdependencies and constraints. And it says, how much money can this make in a week? And people do the calculations. Unless they make a mistake, they get to $1,500. And that just means that they ignored capacity constraints. Because if you look at the calculations there, I know it's a bit small. Machine B will require 3,000 minutes to make all of P and Q. You only have 2,400 minutes, so you really can't ever get to 1,500. Well, then the question is, well, which one should I produce? P or Q? And with the remaining capacity, whatever I can produce more of then. And of course, the example has been set up as a trap. Because when you look at it, Q has the highest price. It has the highest throughput margin or gross margin. It actually has the lowest labor time. So let's try and make as much Q as we can, and then we lose $300. It's damn. So now Ellie would ask us, what are you going to do in this business? Well, unless I can increase the price or I can get more capacity or I can reduce the cycle times, this business is a loss-making entity. I said, well, what if you just for a moment ignored all the standard rules of making a decision around product mix, and you just did the opposite, try to make as much P as you can, and with the remaining capacity you make Qs, and suddenly you make $300. So fast forward, in 2004, I am in a very privileged position where I'm leading an implementation of theory of constraints at Cisco Systems. They were the most valuable company on the planet at that time. I'm given 20 of their top people. One of the people that's there, I'm told he's on the spectrum. He's the chief architect of the internet operating system. He wants to be trained up, but he's not going to interact with you. He will never look at you. Just don't mind him. You will learn. And I'm going through, the person never looked up, just sitting behind his computer typing. We get to the P and Q, and I'm trying to sort of be interactive and say, this is something that you should all try, see. And I'm like looking at the guy, and it's like, even you, Mac, you should try this example, see if you can get it right. So I present a case, and I said, what will happen? And I mean, these are people that were genius level. All of them make the same mistakes, right? They either ignore the capacity or they pick the wrong one. And I show the right answer, and I'm feeling pretty good about myself. And suddenly, this guy puts up his hand, and he says to me, is the law that you've just mentioned, which is to profit maximize, you have to produce the products not with the highest gross margin or throughput, but with the highest gross margin per constrained resource. Is that law of economics always true? Because if you do the calculation, you find that if you're producing P, you get $3 a minute. You produce Q, $2 a minute. Simple heuristic that you can apply. And I said, well, it's called the law of economics for a reason. They think it's generalized. But at the end of the day, you have the simulation now. Go and play it. See if you can discover a scenario where the law doesn't apply. I go back to my hotel room. I set up the simulation. I run a query. I'm running millions of permutations. And then 3 o'clock in the morning, I discover one that's deeply disturbing. I phone Ellie immediately. What happens if we increase the cycle time on D just from 15 minutes to 25 minutes? It's a non-bottleneck. It overloads D, but not to the same degree as B. So the loading on D now is 750 minutes, but the loading on B is still 3,000. What would you do? Would you still follow the same rule? The throughput per constraint minute hasn't changed. It's still $3 and $2. What would you do? My intuition was you would do the same. You'd go for P, and then with the remaining capacity, you'd go for Q. If you try to do that, you lose $1,680. So just imagine that. You have a business that's making $300 profit. One of the operators retires, a new person comes in. It's a little bit slower on a non-bottleneck. Rather than taking 15 minutes, now taking 10 minutes. And your company goes from making $300 to losing $1,680. Do any of you have intuition to be able to predict this? I didn't. I will never have that level of, it's just two-way off, right? Now, can you make money? If you go to try and produce as much Q as you can, suddenly you're losing less. That's a little bit better. And we're now losing $300 and not $1,680. I phoned Ellie up. I shared with him the example. He said, it can't be true. We got into a big argument. I showed him the results. He said, well, it can only be an exception. And I said, I don't think it's an exception. I think that it's the more general case that when you've committed to a goal that has overloaded one resource, Because by design we balance capacities, or by debottlenecking we end up balancing capacities, it's very likely that you have overloaded more than one resource. And if they are interactive, you now have a chaotic system. The simple heuristic doesn't apply. Please, when you teach this in future, please teach them this part. It's really important. Can you make money? Actually, if you apply an even simpler heuristic of, say, think about what you would do. You don't have enough capacity to supply everybody. What would you do? You try to be fair and say, let's supply everybody with 80%. So we'll do 80% of P and 80% of Q. That gets you down to break even. But there is an optimum solution that you can get to about 120. And from this, I formulated a new law of economics, which I presented at the TOC ICO in 2006. It doesn't seem that many people have paid attention to it, but hopefully one day they would. But the law is basically saying that the key thing is to produce the product mix that doesn't give you the highest gross margin per constrained resource, but gives you the highest utilization rate of both constraints. So you can see the utilization rates of both of the B and D in this product mix is close to 100%, whereas all the other ones, the utilization when you combine them is significantly below 100%. So fast forward quickly to Tata Steel. I'm the auditor on the project. I get a call from our project manager, Henry de Priya. He said, Alan, you're pretty good at building models. I'm not so good. He said, the guys have built essentially a massive P&Q model for steel products. They're trying to find the most profitable product mix because that's something that Ellie had advised them to do. Switch over to those products when you are capacity constrained that produces the highest throughput per constrained minute. They did that. I said, and what happened? He said, well, it's showing that they will lose money. And we think that they've made a mistake in the model somewhere. And immediately, I just realized it's either a mistake in the model, so I will check it, but what if they have discovered a situation where there's interactive constraints? And that's essentially the case with a V plant, is you have interactive constraints. So I'm going to hand back to Bimlendra to share with you some of the really interesting insights for both him and his team, but also for us that we've learned from the steel industry and applying, building essentially dice games and P&Q models on steroids, right? So rather than have one product and 5 processes, you are modeling a whole supply chain from the mine to the retail with tens of thousands of SKUs and millions of SKU locations. What will you learn? He will use some terms for those that are not familiar with steel. So you're making iron on the left-hand side. Then you start making steel, you mill the steel, you get hot metal out, and you end up finishing it in various different ways, and that gets to the end product. So let's switch back to Bimlendra to hear some of the insights.
Alan has asked me to pick up a couple of examples where digital twin gave us either an advance warning or a methodology where we could potentially use the insights from the digital twin in order to gain for the system as a whole. The easiest example that comes to my mind was the one that was done in the steel melt shop in LD1 in Tata Steel. It was very clear from the digital twin that even though our average was 58 to 60 heats a day, on some occasions we had crossed 60, but those were rare occasions, and just a few times we had just touched about 65. The simulation model showed us that it was technically possible, at least once a year, to have 71 heats. And of course, it showed us at different points in time which ones would be the constraints that would emerge, either due to a breakdown or a plant shutdown. So, for example, a caster could be under shutdown, or casters are running, but their ladle furnaces are under shutdown. Now, this gave us an advance warning what to do just in case a ladle furnace was down. Everything else was fine. Now, we could plan in advance the quality of heats that did not need to go through a ladle furnace and still satisfy the customers. Thereby, we could fully exploit the casters that were already available and the heat that was made available from the furnaces. These are easier examples, but what we also did was that we started measuring ourselves on a daily performance as a gap against 71 heats. This Pareto analysis over a period of time started giving us insights on systematic causes that were there. The advantage was that within 1 month of this analysis having started, we hit 71 heats for the first time. And then we repeated that the second month and the third month. So what was possible even by the simulation model as once in a year phenomena, it could become more a matter of habit to succeed. Now, the more difficult examples and more counterintuitive examples of subsystems actually coming into the play comes from uh, our experience at Tata Steel UK and at JSPL. Now, you remember Eli Goldratt's famous example in operations is about V plant, where steering occurs. Let me tell you that our experience of the V plant was slightly different. What is happening in V plant is not the issue of measurements. What is happening really over there is that every node in a V plant acts as a subsystem. Now, something that happens at a subsequent point in the system always puts back pressure on the previous node. So let's take an example of a system like JSPL, where we knew that the highest amount of money that is to be made is from the plate mill. And in the plate mill, the highest amount of money that can be made is through the heat treatment. Now, heat treatment, we could subordinate everything else to that. You could decide how to exploit that constraint, subordinate everything else to that. However, we found that multiple number of times we were simply not able to exploit this constraint. And the reason was not lying within the plate mill. It was lying in the steel melt shop where the casting schedules were there. Now, in these casting schedules, what was happening was that you would know that in TOC, we say that let's make a pull based system. When you make a pull based system, you wait for the orders. However, not all customers have the same tolerance time. And if you were to wait for all the orders, you would never ever be able to satisfy all your customers. Now, that is why there are multiple methodologies that are used in a steel plant, not just made to order and made to availability, but there is also something called as finish to order. That means you differentiate the liquid steel into a solid form and then you wait for the order in order to process it further. Now, this creates an interesting scenario for a steel melt shop, which is otherwise not a systems bottleneck. What can happen is that if you take too long a period, then you have to resort to forecasting. If you take too short a period, you are too late. Simulation model actually showed us that not only the chaos curve of the middle path is workable, but it approximately rests between 7 to 10 days. That if you were able to pick up any consolidation of orders between 7 to 10 days, the system was in a far greater stable state. Now, similarly, when we did the whole supply chain analytics for Tata Steel UK, we found that the subsystem, which was not a bottleneck for the system as a whole, was the hot strip mill, because there was downstream color coating facilities or galvanizing facilities which were going to auto industry, etc. Though that was the one that was spinning money for the company. However, there was one cold rolling process that was a link between the hot strip mill and where the value addition was taking place. If by chance this link was down, there was sudden rise in inventories. Now you could always plan for such eventuality by keeping buffer stocks. But what if this eventuality is not only highly unpredictable, there are more number of such instances. If they get clubbed together in a short period of time, the amount of inventory that you would create would overspill even onto the roads. Now, if you go by the classic TOC methodology or lean methodology, stock production, you do that, you completely kill yourself. Because remember, every node is a constraint in a way, in a V plant. This is completely different from an A plant. There, of course, overproduction hurts you. Here, everything after you have taken it out from the ground as iron ore or coal, every step of the way, you can add value. In fact, when I had mentioned this to Eli, he had told me that I will show you that you're sitting on a gold mountain. And I do believe that that gold mountain is discoverable through this process of simulation. And all these examples that I have told you, there, the subsystems have never ever been in the focus from a TOC perspective the same way as we were able to look at them from a priori, from the system perspective with all the simulation of uncertainties. And by doing that, we were able to prepare for the transportation better. We were able to prepare for the time period for which clubbing of the orders should be done. within the subsystems, we were able to design the inventory norms differently compared to what we designed for the system as a whole. So I guess these examples should help serve some lesson for all of us that system level constraints are not sufficient, certainly in V-plant scenarios, and certainly where every time you touch a product, you are actually adding value to it. And therefore, non-production does not always give you the best result. Thank you very much.
So just again, why digital twins? It helps us to consider all these VUCCA conditions. As you heard from Bimlendra, subsystem constraints is not necessarily we don't have enough of it overall. We might not have enough of that resource at the time when we need it. So today we have built a whole range of these digital twins. They are supply chain, manufacturing, retail, mining, and projects. They all work in exactly the same way, basically. In the past, it used to take us about 3 to 24 months to build these digital twins from scratch. Today, we can build them, and it might sound like an exaggeration, but we build them within 3 to 24 seconds directly from data that's already sitting in the IT system. So in the IT system is already all the data that we need except for the randomness. That is added on top of the data that we're reading in. So in manufacturing and supply chains, it would be bill of materials, demand forecast, actual supply lead times, and then all the variability around it. In a project digital twin, it would be the actual project portfolio with all the interdependencies, the tasks, the costs, etc. So they all work in exactly the same way. We read in the data, it instantly builds a model. If you give it data for one product made at one factory, sold to one customer, it will build a digital twin of that. Or you give it data of everything from the mine to the retail, everything in between, it will instantly build a digital twin for that. So that was a major example. There's a couple of things that I want to highlight. I've included a lot of slides only for those geeks out there that are really interested in the details. So I'll just skip through those because we have limited time. But some interesting things for Tata Steel UK. Imagine you're walking in like Bimlendra, you're losing £1 million a day. To convince your shareholders not to get out of it, you have to essentially make about £1 million a day. So there's a huge gap. And essentially what Bimlendra started doing is he started to fill in the gap. What are the problems that we have to solve to close that gap? And we were using the simulation model to validate to what extent that problem exists, to what extent we will improve operational and financial performance if we can close it. There's some interesting examples of how it allowed us to challenge industry paradigms. There's an industry paradigm within steel about ton dishes. It's about $5,000 to change a ton dish. So you typically want to run about 5 to 6 heats before you change it, sometimes 11 heats. Just for those that understand, we went from about 55, 58 heats per day to about 70 heats a day. One heat, $33,000 of additional net profit, right? What we found interesting is we said, what if we switched over to only producing what we are selling? But now we have to challenge this batch sizing policy to minimize the cost of a ton dish. What you see on the right-hand side here is that actually switching every single heat, which is the most extreme case, our profits go up and the cost per unit actually comes down. But only if you calculate cost per unit based on tons sold divided by total cost rather than tons produced divided by total cost, which is a common mistake. So many examples here that I can share. Jindal Steel was our latest case. Bimlendra was CEO at the time. We get called in by Naveen Jindal, that was the chairman. And he said, I want to grow the steel business. There's a huge opportunity within the Indian market and surrounding in terms of infrastructure. We want to grow from 10 million tons, or about $10 billion in revenue, to 40 million tons, 40 billion in revenue. And his question to me was very simple request. I don't want surprises. I don't want subsystem constraints. Make sure that I have enough capacity in terms of the capex that we've invested. Make sure that my inbound logistics is not a constraint. Make sure my outbound logistics is not a constraint. Make sure that we are properly synchronizing the scheduling when there are interactive constraints. Because you can imagine as you go up there, you're ramping up capacity, right? You buy capacity in big chunks. One day the caster is a constraint. Now you're releasing the new casters. The constraint moves the upstream or downstream. So we ended up building 4 digital twins. But just to give you an idea in terms of a map, that's what their demand and supply pattern look like today. This is what it looks like in FY30 when they're doing 40 million tons. Dramatic change in product mix, in what is demanded, at which locations, what is produced, etc. way too much complexity to be able to cope with this. And that's one of the reasons why we ended up building 4 digital twins for them. We had a full supply chain digital twin all the way from the mine to the retail. We had very detailed 3D models of the raw material handling coming in to make sure that that never becomes a constraint. The outside rail operations of trucks, the shunting locos, make sure that that doesn't become a constraint. And then the detailed caster scheduler. As I mentioned, I've included a lot of slides, but essentially going back to that dice game and P&Q, that's all that we did. We just built a dice game for them and a P&Q for them with a lot more details. And the benefit of the self-configurable digital twins that we developed is they were up and running within a couple of weeks and we're getting insights from the models. And what's very exciting is they're now using the supply chain digital twin as a key part of their sales and operations planning. So every month the team gets together, all the marketing and sales people put in the range of what they think they will sell by product category, by region. Minimum, that's what we've already committed to contracts. We have to produce that. Maximum, this is what we can sell up to. And it will run these optimization engines and find the most profitable product mix. But it won't stop there. It will then simulate that in the supply chain under real-world conditions for the next month to see if it's actually viable to produce that. So it's a difference between doing that P&Q calculation statically versus actually simulating it and see what will happen. So it's been major, major insights. Like I said, there's way too little time to take you through all the insights, but what I'd like to share with you is just the last part here of what are the big lessons here. So dynamic simulation models are simply superior to our own intuition. As soon as you have 2 or more of those VUCCA conditions, you should really be checking yourself. Do I have enough intuition to make reliable commitments, to predict the impact of changes, and to make good global optimal decisions? It enabled substantial advancements in the TOC applications themselves. So we are constantly checking, we're running optimization to see, can we improve the DBR algorithm? Can we improve the demand-driven replenishment algorithm? Can we improve the CCPM algorithm? What is the best mechanisms to control WIP, etc.? And I want to end off in the last few minutes just with a slide that I think sort of captures my insights over the last 30 years of applying theory of constraints. I was presenting this recently to the Platinum Group for Tony Robbins. It's a group that pays about $150,000 a year for coaching. And they gave me an opportunity to say, how would you present theory of constraints in one slide? And I realized that to maintain focus, you need to think about one-to-one pairings in the same way that it was a discovery by Ellie that think strategy tactic, don't think strategy tactics. There's a strategy as the objective that you're trying to achieve. Tactic is the best way of getting there. How do I maintain that one-to-one pairing throughout? I have a goal. There's work that I have to do to achieve the goal. The work follows a process. I need resources to man the process. The goal puts a demand. It tells me what I need of each resource, and then I can compare it with what I have. Any resource I don't have enough of is a constraint. It's a flow rate constraint. If I get more of that, I could have more of the goal. But there's also a flow time constraint. Sometimes I have enough, but I'm not doing it fast enough. So now I'm plotting out my total lead time there. Can you notice the little cycle times of ABC as a small fraction? The majority of the time is lost in backlog or queuing. And I'm going, what's my flow time constraint? So I end up with what is the constraint. And this could be at a system level. It could be at a department level. It could be at a process level. The goal of the system is placing a demand on my department. What don't I have enough of? Then I go one constraint, one problem. There's now a gap between what I have and what I need. Pareto principle applies. It's fractal. It applies on itself. What does it mean? 20% of 20% will give me 80% of 80% of that gap. I can apply it again. One problem typically explains 51% of that gap. That's the one problem I'm looking for. Simulation is a great way to find out what that one problem is. Now I have the problem. I now go to the next pairing. One problem, one conflict. Problem solving is finding a solution to a problem. Innovation is finding a solution to a problem without trade-offs. Writing out my pro-con cloud in the form of, I feel pressure to implement the solution to solve the problem, but I have an alternative, either the status quo or another alternative. Each of these options have pros and cons. The listing of the pros and cons help me to understand the trade-off, helps me to understand why we get stuck, why we might overreact or underreact. And then I'm going to the next pairing, which is now I have one conflict, I'm looking for one innovation. Find a one thing that can give me all the pros without any of the major cons. That's true innovation. That's what's embedded into our pro-con cloud method. Is what's the important problem? What's the conflict? What's the innovation? What's all the yes buts from the stakeholders? What do I have to add? And then I go from innovation to one experiment. I'm doing the experiment, I'm testing out this innovation, and that's again where the simulation models come in, because they can allow us to test that hypothesis about what the solution is to the one problem in a very low cost, low risk way without taking major risk for the company. And what I want to check is the problem solved? And if it is, then I repeat the cycle. Next problem or next constraint. And I can apply this process at the system level or any subsystem level. I hope that makes sense to everybody. If you're a subsystem, doesn't matter how big, the question is, your goal, you can't determine the goal. The goal has been decided on. You have to understand that goal puts a demand on your department or your process. Do you have enough? Are you doing it fast enough? Which constraint do you have? Do you have a flow rate constraint where you need to do more? Or do you have a flow time constraint where you have to do it faster to meet the requirements of the system? Regardless of which type constraint, what's the problem? Either the problem that's causing you to lose throughput, we must stop doing this, focus on the highest value added, or simply get more. It's an elevation conflict. Or if it's a flow time constraint, what's causing the most delay? And that's the cycle that we go through. So I hope that was useful. Unfortunately, we don't have time for Q&A, but I'm going to be available. And I'm looking forward to all the comments and questions. I'm sure that there's going to be a lot of challenges as well. But I want to leave you with this. Our intuition is simply not strong enough to understand all the VUCCA conditions. And this is where simulation model can become a huge, huge help for all of us. Thank you.